Hey guys.
Morning, everyone. Look at that. We have Max and Mike talking. Excellent. Next week we have a blue spec talk, so that should be also interesting. I guess we give everyone the requisite 20 more seconds. The different camera angles give you a really different look.
Yeah, is it me or are you talking about me or
Yeah,
John?
yeah, you.
Oh.
Your
I mean,
other
like
your other join with its stock photo.
Oh. I get the joke. I've come around. Yeah. Gotcha. Yeah.
So are there any top of mind things anyone wants to bring up?
I have a PR out to add CIRCT to Compiler Explorer, so we'll see how that goes. I'll update once we actually get it in.
And that's
Miscellaneous question. Does anyone know how difficult it would be to expose PyCDE through like a Jupyter notebook? I don't know anything about notebooks.
I think it's pretty easy if you can package the the wheel and put it somewhere.
Okay, so it supports running native code, not just Python.
I think so. Wherever the notebook is hosted would need to have the wheel compiled for that platform. So,
right.
You know, you build a mini Linux wheel, you should be able to run it on most Linux hosts, kind of thing.
Okay. Starting to proselytize it inside Microsoft. So
yeah, cool.
We're going to have to start talking about behavioral constructs at some point soon. That's what Morten and I were discussing late last night.
Or early, my morning.
That was your lunchtime.
Yeah.
all right then.
Good to go?
Max, would you like to take it away?
Sure. Okay. I'm going to try to share screen on this other computer. Let's see, just to be careful. Okay. Okay, I think you guys can see my slides because I can see my slides on my computer. Okay, so I kind of made this joke when we were talking about scheduling presentations that if I presented, it'd be not very substantial, significant, because it's kind of like I've been working on this project that's kind of like baby's first FPGA project because I had no idea what I was doing. So yeah, so I'm a PhD student nominally at University of Chicago. I say nominally because I've been bouncing around internships for the last year. So it's like, am I a part-time PhD student? Am I a part-time software engineer or FPGA dev, whatever? And these are my closest collaborators. So Ryan Card, Kyle Chard, and Ian Foster is the PI, and this project's in collaboration with Argonne National Lab. So the TLDR, and there's an asterisk, I'll explain in a second. The TLDR is, hey, I have a design that does something. The asterisk means, first of all, this is old, this is from about a month ago. And second of all, is hoping to have more recent, better results. And yesterday I managed to blow away /bin and /lib on my synth workstation. So I don't have those. Anyway, so I gave this talk. This is the second time I'm giving this talk. I gave it for the first time kind of like a rehearsal talk to my research group. And I called that one 7 Circles of FPGA Dev Hell. And so I changed the leading slide for this because you guys are all familiar with that story. But this slide still is good for an outline. So this is the basic trajectory, the lowering path for what I'm going to describe, a neural net that goes from PyTorch to, you know, like a net list, synth placed routed net list. So we're going to go through PyTorch. PyTorch is IR, MLIR, a little bit about HLS, RTL, logic synthesis, et cetera, et cetera. Okay, so what's the background? The background is science. We're going to do science. I was looking up memes, and there's some meme from one of the MCU movies. We're getting in losers, we're doing science. So there are some science experiments that have extremely high data rates. So this is not my science experiment, although I'm adjacent to them at Argonne National or Fermilab or something like this. But this is the LHC, and they collect a whole bunch of physics data, 40 megahertz a second, megabyte per collision, et cetera, et cetera, et cetera. They can't store it all because there's a lot of data. So they have trigger systems. They have multi-level trigger systems, which means they look for interesting events in the data. And they run ASICs and FPGAs for the fastest triggers and use some kind of, off-the-shelf hardware, like some kind of computer or GPU or something like that for the higher latency triggers. So the higher level triggers. So this is not my science experiment, but this is a use case for this same kind of work. My science experiment is high energy diffraction microscopy. I'm not a microscopist. I don't do this. I'm just like the code monkey that's trying to help the real scientists do better. So they're doing high energy microscopy, discovering new materials and stuff like this. So they're scattering high energy X-rays and getting Bragg peak distributions. So whatever, here's the physics behind the distribution of Bragg peaks in some image. But the point is, it goes right now at 3,000 hertz, but the next gen will go to megahertz. So this experiment is approaching data rates at which something like a GPU wouldn't suffice. So the current, so my work follows on like the tail end, or is a subsequent or like a sequel work to this work. So the group prior to me arriving implemented a neural network that did this kind of like peak detection, peak fitting. It literally is reporting, right? So the high level is I want to report whether an image has anything interesting in it or not. And the way that I do that is if I can detect this distribution, this thing called a pseudo Voigt distribution effectively. So the neural net will do something faster than the classical method. The classical method is distribution fitting by whatever gradient descent, online gradient descent for each sample. The DNN is already fit, so it spits out two numbers, and if the numbers are not -1, -1, then you have something in the image, keep the image. So this runs at like 25 microseconds latency, which is good for now at 3,000 hertz, but isn't good at a megahertz. So that's the science background. That's the reason that I've been doing this, and I've been doing this for about 6 months. I'll pause for a second for questions before I jump into the meat of the FPGA digital design compiler stuff. No. Okay, cool. So before I get into what I did and why I did it, what's the prior art here? There's a bunch of prior art here. So each of these things on the screen is to some extent claims to do some of these things. So HLS 4ML might be the most like well-known one. It's a Fermilab group, and they do claim or attempt or address problems at LHC. And they go through, so it's a Python package that goes through Vitis and stuff like this. They basically have pre-designed parameterized HLS kernels. Fin is Xilinx's thing, and there's like a close relationship between HLS 4ML and Fin. Fin is more so about quantization, I think. The Georgia Tech thing and the IBM things are abandoned. University of Tokyo, there's a single dude who has just an RTL generator for DNNs where you can feed it a PyTorch neural network and it'll give you something. And then there's a group at ETH who might be collaborating with, might not, that's attempting to do some of the same things. So these are not really alternatives in the sense that they don't really compile anything. They have pre-existing cores that are parameterized. And so I can't actually speak for the Georgia Tech project and the IBM project, but the other four are just parameterized cores. There's no compilation really. The closest things that are out there that to what I am attempting to do, have been trying to do, are two projects that have already, spoken here. So Han Chen, the Scale HLS group, and the Soda Up guys at PNNL. And unsurprisingly, they're going through MLIR just like I am. Okay, so here starts the gory journey. The entry point is, relative to like where we end up, breathtaking heights of abstraction. So here's actually the neural network. It's a very, very small neural network. This is the smallest factor scaling of the neural network. This is a quarter scaling. Take all of the convolution dimensions, multiply them by 2, 3, up to 4, and you get the full scaling. So on the left, you have a representation in PyTorch. Maybe people are familiar with this, maybe not, but it's basically, this isn't Python, but it's close enough that it might as well be. And on the right, you have PyTorch's native IR. So they have something called TorchScript, and they use it to lower to various hardware platforms. Yeah, nothing more to be said about this part of the project. It's all very well manicured and polished and easy to use. This is where we get off the road of simple and straightforward and get on the road to like pain and misery. Not really, I'm making jokes, I'm being like, farcical, sarcastic, but anyway, so we enter the MLIR ecosystem. So this is, a standard representation for convolution. It's pretty recognizable, even if you don't spend a lot of time in the higher level dialects. It's nested for loops, right? So this is going to be the running example for most of the talk. And so what's the strategy? I didn't think it, I presented this in a certain way to my research group, and I said, well, here's the strategy. You unroll all the loops. And I kind of thought about it before getting ready to present here again. I was reconsidering like, why did my strategy has been for, 5 months of the 6 months, just unroll all the loops. I've described it to several people that are on this call right now as I have a fully unrolled neural network, and here are the problems that I'm having today. Can you save me from the problems that I'm having today? But why did I try to do this? Why didn't I use a systolic array or something that's statically scheduled already, some other alternative architecture? I don't know. And the reason is kind of like, I didn't know what I was doing at all. It was pretty misguided. I had read a little bit, knew a little bit about a bunch of disparate things. I knew that loop unrolling in general is good for optimization. Like this kind of really naive perspective on it. Like if you unroll loops, cool, your thing goes faster. Then I read Han Chen's paper, and he has, so the Scale HLS paper, and he has metrics there for the effects of various optimizations in his pipeline. And he gets the best bang for his buck just unrolling all the loops, right? So I'm like, cool, I'll just unroll all the loops and then I'll splat it on the neural network. How hard could that be if I have a big enough FPGA, a small enough neural network? It should fit, it should all go, it should all be swimmingly easy, right? So unroll all the things. And initially, the route was unroll all the loops, lower to standard dialect, emit LLVMIR, feed the LLVMIR to Vitis, and then let Vitis do its magic, right? Mostly because I had no clue. I had no clue. Like I wanted to look at as little of the IR and think about as little of the digital design as possible. I wanted to like stay a neural nets person. That has not worked. So I was doing this, and Vitis will probably, some people are familiar with Vitis on the call. I don't know if Steven's on the call. I told him I'd be presenting. Vitis worked to some extent, right? So like initially I was getting, it would generate RTL and it would generate estimates for the initiation interval, and so therefore the end-to-end latency. And that was fine initially because, so one thing that was immediately obvious is it would take a long time to generate the RTL, like 12 hours, 18 hours, 24 hours sometimes. And when I was first starting out, like I was comfortable paying that cost. Like I didn't know what I was doing. Hey, I just got to be patient, let it do its thing. And eventually, basically the cost got too much to bear. And so I had to think about I had to like introspect and kind of try to perform like, not archaeology because it's not dead, long gone and buried, but like, because Vitis is closed source, I don't really know what it's doing, right? I can kind of inspect the logs. I can kind of guess about what its ancient version of opt does, but I had to think about what is HLS and what is Vitis doing that it's taking so long. Essentially, like I couldn't iterate on my design ideas, the few ideas that I had that I could come up with, because it was taking so long. And also it would OOM like all the time until I got a bigger machine or I got a cloud instance with more RAM. So I had to think about what was going on. I had to think about what loop unrolling really meant, and like how many operations were there really, this kind of standard stuff that like, day one at some real job would teach you. You'd have to learn in order to be able to sink or swim. How many operations, how many multiply operations, how many load store operations. So I don't know, there's some amount in the smallest. So yeah, so this is the joke, right? Like I was always waiting for it to finish. So there's some amount of operations. There's some number of operations, like 300,000 multiplies and adds for the smallest scaling. So that's good enough as a number to think about. And I would look at the IR and I would see things, and I had never seen LLVM IR. I had never seen MLIR before December. I had never seen LLVM IR before December. I like barely knew how to write C++ code. I was just coming off like a Facebook internship where I got to know PyTorch pretty well. And I was, like youthful hubris, even though I'm not even that young. I was like, I could do this, right? So I started to pore over the LLVM IR and I saw things, right? So like store loads, things that I'll talk about in a second, a lot of stuff other than multiplies and adds. So anyway, this led me to question what HLS was. This is HLS on a picture. Most people I think here on this call are familiar with what this is. The kind of proxy for so this is just one part of what I was having to do or attempting to do. I was trying to clean up the IR to make it as simple as possible for LLVM for Vitis to chew through faster, better, not OOM, whatever. And so this is just unrolling, and this is kind of like a crappy plot. I'm going to fix this up for the paper. The bars are the number of instructions. Actually, the lines don't even matter. You might as well forget the lines, right? The left is the instructions. Yeah, sorry. The lines are the runtimes. So just to unroll, you're looking at like 17 minutes for the entire net, which is, so this is an affine, by the way, right? If you want to unroll this net that I have, that is a small net, whatever it was, like 6 layers, 7 layers, you have to wait 17 minutes just to unroll all of the for loops. And the interesting thing is, by the way, that LLVM opt will unroll it much, much faster. I don't know what's going on. So I've looked at the MLIR code. There's some stuff in there. There's some comments in there like we should cache this. We should memorize this. So it's not completely optimized. Not all those passes are as optimized as LLVM's opt because LLVM's opt is much older. But anyway, this is not the longest pass. The longest pass actually was store load forwarding. So you look at the IR that you get out of either my pipeline or any pipeline, really, you're going to see store loads that are kind of unnecessary if the entire loop is unrolled, right? Like I don't need to store to some memory location just to load it in the next, next 5 lines. So I tried to do, I tried to do store load forwarding. There are a bunch of passes, both in MLIR. So that I think I annotated these now, whatever. So affine scale rep is in MLIR, and yeah, and the top 2 are in opt. And these take forever, like 24 hours for store load forwarding for my smallest net or something like that. And again, the problem was not that it did a bad job or that it didn't work. It's that it took too long for me to be able to figure out, hey, if I move this around, it's iteration on its design space exploration, right? I couldn't do it effectively. So the way that this has worked for me is right, like every time I hit a wall of like something's not working, some kind of cost I'm paying because of ignorance, I then have to go through this tough process of like, do I give up the project and stay ignorant? Or do I, open Pandora's box and figure out really what store load forwarding means? And so at every step of the way, that's what I've done, right? Because I haven't given up yet. So store load forwarding, at least, so this is visible in MLIR in this very nice, pretty printed way. I'm sure an opt is doing the same, and LLVM is doing kind of the same thing. Store load forwarding solves constraint equations to make sure that there's no memory overflow, you're not stepping on anybody else's memory footprint. So you have to solve a bunch of constraint equations for a bunch of nested for loops. And even if they're small constraint systems, if you unroll all the loops, you're going to have n squared or something, n cubed, where n is the number of, I don't know, n is the actual trip count or something like that. So that takes forever. So again, this isn't really germane, like it is 0 or 1 integer programming and it is NP complete, but those constraint systems are so small and they're actually solved using not Gauss elimination, Fourier-Motzkin elimination. So but anyway, whatever. So it's a hard problem and it's solving, hundreds of thousands of hard problems for me per lowering. So what am I going to do about this? There's no way around it. I essentially could not end up using either opt or MLIR to do this in a rigorous, principled way. Essentially, like the compiler is conservative. Either of those two compilers are conservative. They have to solve the constraint equations. As far as I could figure out, there were no pragmas that I could pass it that would let it, hands off the wheel. You know what you're doing. I'm going to unroll this for you blindly. Sorry, I'm going to store load forward for you blindly. I think the pragmas do work actually for loop unrolling in opt, but I didn't find any for load forwarding, and I might have missed it. But anyway, so what's the alternative? I'm not going to do any of this. I'm not going to actually compile my program, and this is a little bit weird. I kind of deliver it with some gravitas when I'm talking to people that aren't familiar with this space, compilers at all. I'm going to interpret the program. I call it abstract interpretation. I use all these fancy words again, just to drum up hype. But what I'm going to do is I'm going to run the program, and I'm going to run the neural net, which is, the program that represents the neural net. And instead of trying to, so it's definitely instead of evaluating the multiplications and the adds and trying to compute a result from the neural net, and instead of trying to do analysis on the IR, I'm going to do the dumbest thing that I could think of, which is I'm going to emit the IR, the LLVM on the IR that I want, that I know is safe to emit, because I have a high level perspective on these operations, these stores and loads. I know when they step on each other and when they don't. So on the left, you see structured control flow dialect. And on the right, you see Python code, which is what I generate in direct correspondence with the structured dialect, structured for loop dialect.
This is exactly what you do with PyCDE. So this code would almost work off the shelf with PyCDE.
But you're going to generate. So when you say it works with PyCDE, what do you mean? What does it do? What does it do?
So this is Python code. It runs the for loops in Python. Yeah. And then we'll synthesize all the infix operations to circuit.
Yeah, God damn it.
I mean, yeah. This is, thematically, this syntax works, not, you'd have to change a few things, but yeah.
Yeah, it's fine. I'm not surprised. Again, I don't claim to be anything but I don't know, persistent and stubborn. I didn't think that I invented it. I'm not Curry or Howard, and I'm definitely not Mr. Abstract Interpretation. Anyway, so I'm going to look at that and maybe I'll talk to you after, John.
Yep.
But anyway, so what do I do with this? I literally just, printf, print LLVMIR, it's unrolled. The one nice thing, so what can you do with this, right? These, just like John, I think, is alluding to, hey, these infix operators, I'm not actually going to do addition. I'm actually, unless they're on loop bounds, right? So these VI6 things, those are evaluated. I think that's on my next slide. Yeah, those are evaluated. The other operations, so the floating point operations, are not. I'm just emitting code. The one thing that I'll say is a little bit more subtle than it might appear, is these square bracket things are classes. They're memref, quote unquote, memref classes, and this is how I'm doing data flow analysis. So each of these reads is a read from, you can think of it as a register, right? Like this is I think this is basically what LLVM does to create SSA instructions. I'm going to push to a location, like a named symbol. I'm going to create a named symbol when I add to a quote unquote memref object, and when I fetch from the same tuple of indices, I'm going to get that symbol back, and that allows me to funnel like data, like values, right? So tracking the results of operations throughout the entire neural network.
So this is essentially a multi-dimensional array lookup?
Yes.
If I'm interpreting? Okay.
Yes.
Yep.
Yes. Exactly.
Yep.
Yeah. In fact, in my latest hacking on this actually stores in a NumPy array, so I can do slicing on that array very nicely. Yeah.
We
so
actually have support for NumPy multi-dimensional arrays.
Well,
in PyCD.
Yeah. I'm not surprised I missed like the glaring omission. Anyway. So yeah. So you know, call them, you know, cutesy name, geometric symbol tables. Hey, I'm going to index into a symbol table instead of giving it a name. There's no real geometry that's in play as of yet. Like I'm not doing some kind of data reuse based on, I tried, but I wasn't able to pull it off, data reuse based on proximity of indices and stuff like this. And so cool, now I have LLVM-IR and it's as clean as it can get. It's literally just multiplications, additions, what else? I don't know. I had this fake op called a ReLU, whatever. Sorry, not a ReLU, because I wasn't making up my own ops at the time. But it's the cleanest IR I could have fed to Vitis, and yeah, no dice, right? Like it's doing something. It's doing something really tough. I don't know if it's doing it like in a crappy way or it's just a really, really hard problem, but it wasn't working. So just you know, interlude, are there alternatives? So when I presented this to my research group, I primed them with like, at some point you guys are going to think I'm insane and that I had blinders on and I should have taken a look outside of my room to see if there were any alternatives. And there are, of course, alternatives, right? There are other HLS tool suites. So, you know, Quartus, I think, has an HLS thing. John, you can comment on that. I think, John, you're a big like Intel guy, right? Intel user. Yeah. So Microchip purchased Leg Up from University of Toronto. Panda. So 3 of these of the 4 on here are closed source. And again, one of the problems that I had was like I had no clue what I was doing, and I really wasn't like enthusiastic about reading like 15 years of research literature to find out why Vitis was too slow for me. And so no open source to look at except for Panda was kind of difficult. It was kind of difficult so it felt like it was kind of difficult to figure out. So Panda, on the other hand, I guess the software project is called Bamboo and the group is called Panda. I don't know. It's out of some university in Italy. It is actually a fully implemented open source HLS tool that works okay. It also croaked on my code, you know, more often than not, so it didn't save me. But it was still good. It was still good as like a sanity check, like, hey, what is Vitis doing? Vitis isn't telling me anything. Let me put a breakpoint at the best place that I could think of inside Panda to figure out what's going on. So that didn't help. But anyway, this last one on the screen, I don't know, honestly. Like I can't afford this one. I'm pretty sure this one's like really, really expensive. And I'd be interested to know if the more expensive tools are better at this kind of thing than Vitis and Quartus or whatever. So this didn't work. HLS didn't work. And so I'm again at this point where like I have to learn what HLS is doing. I have to learn actually RTL. I have to learn about digital design. I can't just like play in these upper whatever spheres of abstraction. So what is HLS doing? Again, this is the same picture that I had before. Everybody's very familiar with this. The hard part of this from the perspective of somebody who doesn't know anything actually is, I think, the scheduling, right? The scheduling, which is like a complex, difficult optimization problem, and isn't just a matter of hacking, but like formulation of the problem, having a solver that solves the problem. It's a math problem, right? Like the rest of this kind of stuff, like generation of RTL, extracting the finite state machine once you have a scheduled IR is hacking. Like you could kind of do it without really understanding things, and I did. When I was first generating RTL, so what I started doing was generating RTL, right? Ditch Vitis, generate RTL. The way that I did it, like the first couple of times, was I basically copy pasted what Vitis had been generating, and then I just like pattern matched. I saw, hey, the FSM is being generated, has this many steps. I'm gonna write a for loop in a Python script, like this, the dirtiest, ugliest thing. I'm gonna write a for loop in a Python script, and then when it emit that RTL, and I'm gonna match it as closely as I can see Vitis, what Vitis is doing. Even if I had no idea about God, what's wrong with me? Procedural, like combinational or sequential logic. I saw the star and I saw the pos edge clock, and I can kind of tell that those were different, but I didn't know why. I just, oh, these registers are updated in a combinational block, in a combinational whatever procedure, and these are updated in a sequential block. I'm just going to emulate this, right? So you don't need to know how to solve math problems. To write the scheduler, you need to know how to solve math problems. So I kicked that can down the road for a good while, because these are the things that you have to do. It's funny. I've been talking to a bunch of people in this group. One of the people that I spoke with was Julian, and at some point I ran by Julian this idea, this like cockamamie. I thought it was a cockamamie idea, like, hey, I have this basically, like, I have this data flow graph. I can topologically sort it. Why is Vitis taking so long to schedule this like dead stupid code? There are no cycles. There's like the FSM that Vitis would always generate was always this like incremental step through the states and then loop all the way back around. So when it would figure out what needed to be done, it always figured out the most simple thing possible. And I was like, why is it taking so long? Oh, okay, cool. I'll just write that thing. I'll just write the thing that generates a topological sort of the data flow graph. And then I like made up numbers for latencies with no kind of like understanding or concern for pipeline registers or pipelining or anything. I'm just like, I need something so that I can make it through Vitis, so I can get to the next step of whatever this is going to be, but logic synthesis. But so I wrote it. So it ended up being that I wrote an ASAP scheduler and it didn't even know it, right? So Julian had told me something like, he said, yeah, that's a reasonable approach, but he didn't put a name on it, so I didn't know that this was an ASAP scheduler. Well, it turns out it's an ASAP scheduler. And it worked okay. I'll get to why it wasn't the answer, and this isn't a home run yet. But anyway, you need to ultimately solve, like I was trying to say, that this is the hardest part of HLS. You need to solve the scheduling problem. So I kicked the can down the road for a long time, and then like a month and a half ago or something, I just took another look at Julian's scheduling dialect, and I had put enough pieces together in my head, or maybe it was complete and it was completed and it hadn't been completed before. But anyway, I hooked up the LP scheduler and bam, I got a schedule. Like I fed it IR. So this is where I come into contact with CIRCT for the first time. I use CIRCT's scheduling infrastructure to schedule. I'm still generating like goofy MLIR IR from my emitter, but I'm now not generating LVM IR to feed to Vitis. I'm generating MLIR, barely legal MLIR to feed to CIRCT to get it scheduled. So the ILP on its own, I think Julian and I basically figured out it wouldn't work, right? Either it would exceed resource usage, or I don't know. Basically, it wouldn't. The main problem is if you just schedule using ILP, there's no bound on the resources, right? There's no constraints in the formulation of the ILP that say, hey, here's the maximum number of floating point multiply cores that I have, or DSP instances that I have, or whatever. So you have to have something with constraints on the number of resources. And it's kind of like, I'm a little bit mathematically literate. I have taken an optimization class. Again, I was just lazy to like think about those things. I like, hey, job shop scheduling with resource constraints. And then I finally hit upon a formulation that was clean enough for me to understand. And I even found an implementation in OR tools that was clean enough to emulate, to copy. So I have a PR up in CIRCT that I have kind of let rot a little bit, I guess, because I've been a little busy, but for resource bound scheduling of IR, right? So you give it the latencies and you give it a number of instances you have, and it'll schedule something. So this thing, so the PR is up and it's not landed because there are still a couple of things I need to do on it. I, of course, had been running it when I was still keeping up with it on my stuff. And it basically takes too long, right? Like too many variables. So the ILP finishes, but the CPSAT, even though I'm used to CPSAT being pretty fast. So our tools constraint solver is pretty good. It doesn't finish. And I don't know why, you know, again, another black box I'd have to open up. How do CPSAT solvers work? But there's a thing that occurs that again occurred to me kind of like in a naive way. If you look at the IR, just from looking at the IR, you see something that lends itself to kind of like, I don't know what to call it. I call it processing elements, but like grouping of operations into a set of dependencies, right? So one of the things that Julian told me was ILP won't give you the right schedules because, sorry, it'll bust through resource budgets because you can't encode them. But if you encode them using some heuristic, like a linear dependency on the ops, right? Like, hey, this one has to come before this one, and this one has to come before this one, and all of these follow in a train in a line, one right after the other. That set of constraints can bound the number of resources, can be used to bound the number of resources, the amount of resources. And so what's the train of ops that I'm gonna bound together, that I'm gonna line up one right after the other? It's obvious, right? It's the multiply accumulates. And if you look at a neural net, this is one of the convolution. It's the title of the slide is fattest convolution, because kind of what I'm thinking, the way that I imagine it is, I have a high watermark of F max going at any moment, and that's the widest part of my net. Each one of those F max corresponds to a processing element, where all of the operations that are handled by that processing element induce dependencies on those operations. So one must follow after the other. And using these auxiliary dependencies, and Julian's thing allows you to add auxiliary dependencies to the scheduling instance, it works, right? So like the LP solver will finish, and I will get scheduled IR, and it'll be resource conscious. So like, I think, yeah. So in my next slide, I have this like, diagrammatic representation of my brain. This is kind of like, this isn't even logical grouping, right? I don't have modules for these units. This is just conceptual. But conceptually, I have processing elements, and each processing element has 4 things that it does. It takes a ReLU, it does a neg, it does a negation, it does a multiplication, it does an addition, and operations that are handled by these processing elements must follow in sequence after each other. And this enables me to bound the number of resources by, hey, how many processing elements? So for the smallest scaling of my neural net, that's determined by my fattest layer, and that's 36 by 36, 1296 processing elements, which turn into about 2,500 or something, I don't know, DSPs. Okay, so let's see. So there's a couple of little kind of trivial things. They're not very interesting, but one thing, and I talked to Skylar about this, is like, there's a layer where you have to do a softmax, which means you have to add up exponential. So you have to exponentiate and then add up all the results of, it's not the fattest layer, but it's somewhere, right? So for scheduling purposes, right, you don't want to do this in sequence, right? If I think it's like 2100 or something like that. It's 300. It's 3 times 648, whatever number that is. I don't want to do those in sequence. That'll blow up my schedule. That'll lengthen the schedule for no reason at all. I want a reduction tree. Cool. So I'll hook up a reduction tree. Not that complex. Actually, when I talked to Skylar about it, the way that I figured out to talk to him was I was Googling around for this, found an issue that he had made a comment on. I think he posted, right, about whether synthesizers should essentially be thwarted, whether Chisel should do this kind of thing for designers, or if you should let the synthesizer do its own magic and figure out this structure on its own. And from what I understood at the time, and from the conversation with Skylar, I shouldn't actually be doing this. The logic synthesis tool should actually, I should let it do what it wants. And maybe that's true, but as far as constructing the schedule, that doesn't work for me. So maybe as far as like power or area or something like that, I'm doing the wrong thing. But as far as getting scheduled, this is the optimal way to schedule that layer. Okay, so now I'm through Vitis, never mind Vitis. I have RTL, it's properly scheduled. And now I enter the last, the last level of whatever, pain. So the first thing that I got, this is one of the first pictures that I got where like, cool, it made it through, I have RTL, it's legal, it synthesized, it actually placed and then didn't route, right? And I was like, well, on the one hand, this picture is encouraging because I'm getting very good utilization. And on the other hand, I'm getting horrible congestion. So this is against one of these Xilinx devices that use stacked silicon interfaces. So these are 3 separate dies that are connected by VOAs, whatever those really are. And the middle one was always getting congested. And I don't understand this, actually. Like, logically, I don't understand why the synthesizer would always place, and I know what that logic is. It's actually the adds for the softmax layer that I was just describing. They're always getting placed there. And as if like the synthesizer has some sense of time where like it kind of looks like it's mirroring the structure of the net, but that doesn't make any sense at all because like I'm multiplexing all those 1296 DSPs anyway. Like I'm going around and around in a circle on the FSM and I'm hitting all those DSPs over and over again. So like, why is all of the logic for that one layer getting placed in the center? I have no idea. I'm not doing physical design, right? Like I'm letting just so this is Vivado. I'm just letting Vivado do the place and route all its own. I'm not doing any constraint. So that was bad. And this is a nice picture for my research group that don't know about these things. And here's some other funny pictures, like one of the designs that I got all the way through, like 10,000 joules, right? Like it's a 185 watt part. It's like a 185 watt part, and the power estimate was like 10 kilowatts. That's great. So how do I solve this problem? Well, the one thing that I kind of didn't want to, it says here at the top, that this is against FP16. One thing that I didn't want to do, which I knew people do is quantization, because it's not like I'm a principled person, but it just seemed like, hey, that's a last resort. I always have that available to me. And here, it turns out that I ended up basically needing to use it. So I didn't want to sacrifice precision. Not that I really needed or know that I needed for this experiment or anything like that. Again, it was just like an artificial constraint, because if I did that, I felt I should probably use Fin, or I should probably use one of these other tools that claims to do quantized FPGA neural net inference, whatever. And I wanted to be different from that. Okay, anyway. So what do? You reduce the precision. So I had already reduced the precision from 32-bit to 16-bit using Xilinx's IPs. Xilinx has weird, I don't know, again, I don't understand what it's doing. If you try to instantiate a floating point IP using Vivado and you want less precision than 16, so you have to punch in custom precision, whatever, it constrains the exponent to be like, I want to go down to like 4 and 4, right? 4 bits for the mantissa, 4 bits for the exponent, and for some reason it constrains 5 bits for the exponent, and I have no idea, right? Like the GUI won't tell me, and I can't use their tickle scripts either to get something else. I don't know, it doesn't tell me. So what do? I use I ditch their IP and I use a core gen called Flopoco, I don't know how you pronounce it. And the kind of like justification for being able to do this is, hey, the distribution of the exponents isn't that wide anyway. The distribution of the mantissa are kind of weird. They're actually clipped for whatever reason in the already trained net. So I don't, whatever, that's not important. But the 7 bits of precision for the 7 bits for the exponent is unnecessary. It's too much. You can get away with like what, like 4, 5, I don't know. So I use 4 bits for the exponent. And then here's some other kind of like cute hacks. There's one point in this net where you're doing something other than multiplication and addition, and that's that softmax layer. And like operating under the assumption that I cannot dynamically reprogram DSPs to do either division or addition. Like I know that I can flip a control line on a DSP and get it to do, or what, at least with Xilinx's IPs, right? I can flip a control line and get addition or subtraction. but I can't, you know, it's dedicated DSP to like some mathematical operation. So I have to represent all of my mathematical operations in terms of just addition and multiplication. The negation is free because you can just flip the sign bit, right? And the ReLU is also like just to compare. So I have these two operations so I have division and exponentiation. These are the mathematical operations necessary to implement softmax layer. And they only happen once. And if I had dedicated hardware for those things, this would be a waste of hardware. Now, maybe that's not true anymore because I have a bunch of space freed up from using the lower precision, but this is like the back and forth where like I try to solve one problem and wind up in a place where maybe I need to solve another problem, or maybe I don't need to solve a problem that I had solved before. Anyway, so I came up with a way to implement. So implementing exponentiation in terms of addition and multiplication, I mean, that's straightforward, right? Just take the Taylor series of the thing. I'm sure that's what the Xilinx IP does anyway, because you can't calculate a transcendental function anyway, right? So take it out to some, you know, I expanded to four terms. Maybe I need more terms. I don't know. It's fine. Any number less than probably 10, and I'm still good as far as scheduling. The division is the interesting one, right? Like, how do you express division in terms of multiplication? You can't take a reciprocal because that's, you know, that's still division. So there's a famous kind of in the lore trick called the fast inverse square root trick. It shows up in the source code for Quake 3, and then, you know, people talk, I think it was written about in this guy Romero's book, who talked about the heyday of ID development. Anyway, you can basically approximate so if you take a float and you cast it to int, that's some number, that's some bit pattern, right? You can pretty nicely approximate it. Sorry, what am I thinking? I'm thinking you can pretty nicely approximate it using this. So this is like an approximation to the representation, right? So if you look at the int, sorry, I'm saying the wrong thing. If you cast a float to an int, it's some bit pattern that bears no resemblance in principle to the float, right? But if you look at the packing of the bits, the exponent, the mantissa, not the sign bit, it looks like an approximation to the representation. I'm saying gibberish because I'm a little bit underslept. But anyway, if you fit this function correctly, you can implement division as a shift right and a subtraction. Yeah, so this inverse square root trick uses this to do an inverse square root. I don't need a square root, I just need an inverse. So in the inverse square root trick, there's a 3 halves floating around. I just have a 1/2. Anyway, it's a Wikipedia article. This plot I just made. So this is for my data, for my bit width and precisions. And this is so you need to do a little bit of function fitting to get one of the constants. Anyway, it works fine. So there's an approximation involved here, and I don't know how bad that approximation is, but anyway. Okay, so this is the kind of almost the end of the talk and end of the journey. There's like a caveat, but anyway. So after doing all this stuff, I got placement and routing and timing closure. So this is at using 8-bit precision, fully routed with 10 nanosecond, not Fmax, clock cycle. And the schedule comes out to be something like 3,000 intervals. So in total, I'm at 30 microseconds, which is pretty bad because I'm losing to the DNN. But so a month ago, I was so fed up that I was like, I'm done. This is good enough. I'm proclaiming victory. I'm going to write this up as a case study. And this was the slide that I showed. And so like, yeah, so my worst negative slack, you know, hit it right there on the mark. I'm not blowing the budget in any of the single logic, super logic regions. Yeah, no, sorry, period. That was what I wanted. That was what. Okay, so one TBD, and the thing that I was kind of hacking on that blew my bin and lib was I haven't actually been testing. I haven't been writing test benches. Again, just another thing that I like didn't kick the can down on the road. I knew I'd have to do it eventually. I was hoping I could avoid it somehow. Like maybe it magically comes out and it's beautiful and I can just trust it. Maybe somebody lets me get away with publishing this without writing the test benches. But then anyway, so I haven't tested numerical accuracy, and I started doing this about a week ago or something like that. And so one difficulty there is Flopoco has a non-standard floating point. They describe a non-standard floating point implementation, but it's actually pretty easy to emulate. So that's good. So I can reproduce, so I can use my little interpreter to actually evaluate the net using the non-standard floating point representation, and I can get the answers that should come out on the other end of the FPGA. And I've started doing this along with cleaning up the code, right? So the code was a mess. I'm cleaning up the code, and I'm also writing the test benches, and I'm doing all this stuff. So TBD if I did something horrible and this doesn't work at all, but I think it'll be fine. So this is kind of like a point of closure, not complete closure. This is like 6 months, and I got something out the end, not a complete failure. What's left aside from the cleaning up around the shop kind of stuff, like the test benches? So there's John's favorite topic of wire delays, which means that in principle, I think I would like to do physical design, right? Like I would like to place these things according to the geometry of the net. So here's some pictures from Vivado. If you use their P block placement API, you can get stuff like this. I don't know if I'll get to this. There's a guy over at ETH that wants to collaborate on this, but again, like part of me is like, I want to move on to something else, but then again, I don't know, maybe it's still interesting. So I'm done, and I have 8 minutes left. I just want to say, like, the title slide was Baby's first FPGA design, and it takes a village to raise a baby. And here are all of the people that are in this village that have raised me from a baby into like a toddler at FPGA design, right? Like I've gotten on the phone for an hour with this person here, another hour, like Steven, I spent like 3 hours on the phone with over some number of weeks. John, I've talked to, Mike, I've talked to, like I'm being a little effusive, but like this is the quote unquote greatest tech community I've ever been a member of, and I'm really grateful. So that's it. That's the end. Oh, that's funny. I forgot to update the last slide, so I'll leave it here. Yeah.
That's great. I'd be curious how much of this you can do in PyCDE as of the, yeah.
Yeah, I like all things, I have a, like all people, I guess I should say, I have a to-do list, and definitely like checking out PyCDE is somewhere near the top.
I have a small question.
Sure.
What did you end up doing with respect to memory interfacing?
Yeah, so John's inspired, brilliant suggestion, forget memory. I don't need memory, never heard of it, hope I never see her. It's all registers.
Got it, okay.
Yeah.
But you did get some PCI stuff working on Xilinx, right?
Say that again?
As far as I remember.
Oh, Axie. Yeah. So that's funny. So in December, I got Vitis to generate something for me, and I'm like, cool, I'm done. This is done. This is so easy. I just need to hook this thing up to the outside world. I need to talk to it over Axie. So I don't know, as some people remember, I don't know how many people like what the turnover rate, but I gave this little kind of like, help me, I want to talk over Axie, or I want to talk over some protocol to my logic that's on my board. And so it took me like 3 weeks or something to get Axie working to talk to a convolution or something like that. And so I did get it working, but that was streaming. So that was DMA to streaming. So there wasn't any memory that was actually being used. Like there was no BRAM that was being used on the FPGA. So that answers that thing, I think, because that is what you were talking about. Although maybe that's not the most sophisticated answer to the question. But I just want to say, so John, I had a call with John, and John's like, what do you need memory for? Actually, what you said was, why do I have anything but wires at the interface? And I'm like, you're right. Why do I have anything but wires at the interface? And so I don't have anything but wires at the interface, and I don't have any VRAM.
Got it.
Yeah. Yeah, cool. So thank you everybody. That's it for me.
Awesome. Thanks for sharing.
No problem. Thanks for hearing me out.
It's cool to see it at this stage, you know, like after hearing you talking about Axie, hearing you talking about unrolling, and kind of seeing it all put together is really
I'm
cool.
telling you, man, babies, like he's growing up. He figured out like he figured out the next thing.
Wire delays.
Yeah, exactly. Yeah, exactly.
PyCDE, man.
Yeah, man, it's the future. Cool. So one thing that I guess I'll, circuit. So it's funny, the guy Tom talked last time and didn't talk about circuit. So there's that one PR that I got to finish that I owe to Julian, I owe to, I owe to circuit, the scheduling stuff. And then there's the PR that I was talking to Morton about that was kind of goofy and is closed, I guess accidentally, but for good reason anyway. So there's the FSM dialect in circuit. And I was trying to use it like I see Vitis instantiate, creating FSMs. Hey, I have a big top level controller FSM and it's driving all of the other IP, right? And, lo and behold, you can't do that. I guess there are principled reasons, but the code wasn't letting me. I actually don't remember what the change that was necessary, but I pushed up a change and then some discussion with Morton. Hey, that's not a reasonable thing. You probably shouldn't do that. You should feed the wires into the FSM and not so I was trying to instantiate IP as a black. So I was trying to instantiate RTL as a black box in that FSM dialog. And that's the thing that you can't do because of symbol. Now that I remember, it's because of symbol tables and 2 levels deep symbol tables, or something like that. And Morton's like, that's not a good idea. And he's probably 100% right. So my question is, how do you do this? In instances, use cases like mine, as weird as it is, I have a big FSM, let's say it's 1,000 steps, or let's say it's 2,000 steps, and it's just one controller. I don't have anything else. What's the best practice? I know it's weird, like what kind of design is like that? I don't know. But in this case, what is the best practices, smart person, trained person solution?
You instantiate the IP as a sibling to the FSM and then wire it up.
Yeah, okay, but I have, so in this case, I have 1,296 F moles. I'm going to feed in. I mean, maybe that's fine. Maybe it's completely fine, and the compiler can handle, 8 times 1,296 wires going into a module. I guess why not? But that seems a little weird to me.
That doesn't sound uncommon. So in this internal design written completely in System Verilog, we have modules that have tens of thousands of wires heading in and out. Probably more than that.
Okay. Yeah, I mean, it felt like a kludge to me, because that was it's like, cool, I'll just feed in all the wires. And then I was like, oh, maybe that doesn't make sense, because you're just doing a lot of something because the compiler won't stop you from it. I don't know. Yeah, okay, that's a fine answer.
But I mean, it does sound odd that you'd be feeding that many wires into an FSM.
Well, yeah, so I don't think that many designs call for an FSM that top level controls that much IP. That's probably why it seems weird. I mean, just naively, I'm like, I don't think a processor, I can't think of another kind of thing where there's one FSM and it controls everything. But I don't have that much experience. Maybe there are things like that.
I mean, I guess one way to change that would be through hierarchy. Like, can you break things up into sub blocks with their own FSMs that get controlled from a top FSM? I'm just spitballing here, but if you don't want to have one giant FSM that controls everything, one approach to that is to use hierarchy to split things up. Yeah,
of course. I think I get what you're saying. There's really no such, like, it's like step by step, right? Because it's this unrolled representation. It's basically like imperative. I don't want to say procedural, because that has a meaning. So I would be abusing the term, but it's imperative code. First, I evaluate this loop body, and then I evaluate maybe this next loop body, or again the same loop body, but I'm just going loop body by loop body. And because there's not a lot of weird architecture in this thing, other than, like, it's a pretty simple network. It doesn't even have residual connections, right? So there's no like, hey, I'm going to bring this thing all the way from the back, from the beginning up to the top. Just go step by step, right? There's no hierarchy at all. There's no conceptual hierarchy.
Mhm.
Yeah. Again,
Well,
it's a really.
indeed.
Sorry, go ahead.
So I jumped in. So Mike, do you have wanted to add something?
Well, I guess maybe just one quick other potential angle would be in between those steps that have to happen one after the other, instead of having an FSM controlling that, you could have like a latency insensitive handshake kind of thing where the hardware is making sure that the schedule you want is legal, and you trade off, you kind of spread that control logic out throughout the data path so that there's a little bit of, okay, now this chunk can move forward.
But
that's
if
a
I do-
different trade-off.
So if I use ready data valid handshake, would it, you know, I think I know what you're talking about, right? Like some protocol, like either it's ready data valid or it's some other simple handshake protocol. So the latency insensitive stuff is slower in general than statically scheduled, right? Like that's the whole appeal of, if I understand correctly.
Well,
Yeah.
yeah,
And it takes
yes
more
and no.
area.
It takes more area to achieve potentially the same schedule, and it could achieve a worse schedule.
I thought there would be some like latency debt incurred from actually arbitrating the protocol, like the 2 or 3 second, and maybe I have those, sorry, cycles, right? Like 2 or 3 cycles to actually be like, okay, cool, ready, valid. Here, give me the date.
No, it'll just be combinational latency.
Okay, interesting.
And there's
There's
I mean, the flip side, like there's also a control, like your centralized control is going to have Fmax limitations it causes if you're controlling a very large chip.
Right, right. So essentially you should think of ready valid as a distributed controller.
Yeah. Yeah, so the clock buffer or whatever thing reducing Fmax, or maybe it's not the clock buffer, maybe it's just routing the clock lines. Definitely, that's what you're talking about, right, Andrew?
Yeah, like there's getting across the FPGA is going to take at least the whole clock cycle already, right? You're not going to run at a high clock rate.
Yeah, that's a good point. Yeah, that's a good point. So I should think about that. I mean, I guess I intuitively kind of don't have any, I don't have, you know, other than the things that I've just mentioned, I don't have any sense for whether it's the right approach, whether it'll work for this goofy thing. I'm also comfortable like with the idea that like it's such a far edge case because it's such a goofy thing to do that there is no right answer. So there is no good answer. There is an answer, and you eat the costs associated with it because you're doing such an unconventional thing.
I don't fully understand why you need so much control in what should be a statically scheduled thing. So well, I would rethink your architecture a little bit.
So like one question there, to John's point, might be, you don't have to, like, if you have a statically scheduled data flow pipeline, just because your inputs aren't valid doesn't mean you should shut stuff down. Like if you're just like selectively turning stuff along on your pipeline on and off, like you can let it feed through. Like all you need to know is like every 8th cycle, this output is valid, right? Like I don't care that I'm doing unnecessary multiplications necessarily, unless I'm actually scheduling for reuse across iterations of my loop.
Yeah, so that definitely resonates, makes intuitive sense to me, because that's what I've been, that's like in my operating model. It's like, hey, I'm going to get garbage in the pipeline, but I don't care because I only care about the output 3,000 intervals. So whatever garbage it's feeding through the rest of the time, I'm going to ignore it anyway. I guess, so to answer your question, John, maybe the answer to this question is, hey, handshake, but I don't know how to like route stuff like, hey, I have one convolutional result, the receptive field or the whatever you want, the activations, right? And that activation, that block of activations feeds a whole bunch of stuff in the next convolution, but so you have one DSP talking to like whatever 16, right? You have one multiply talking to 16 multiplies, right? And that same DSP, because it's being multiplexed, or that same multiply, that since it's being multiplexed, that 16, that group of 16 changes. So I'll do one convolution because of the PE model where I have a processing element and I group operations, et cetera, right? So I don't have all the freedom for like this in the scheduling that I would if I weren't grouping operations, but I am. So I have this floating point multiply feeding 16 other floating point multiplies. And then the next convolutional layer, it's feeding 16 other floating point multiplies. You know, there's some intersection because that's just how the chips fall. But I need an FSM to say route here on this time step, and then on 10 time steps later, route to these other ones. At least as far as the data path goes, not as far as, I'm not talking about like routing. So I don't know how to do that. I think maybe you can do that with handshaking, but I feel like maybe you can't, because those things have to be adjacent.
But possibly the Mike's point, like if that's a fixed interval, that's local control.
Right.
Yeah.
So you'd have a tiny little FSM in each PE.
Yeah. That tells you where to go.
Right.
So when I was thinking about BRAM, when I was thinking about whether I need to use BRAM, one of the interesting things that I found somewhere on Xilinx's website was that apparently the first microcode implementations used essentially BRAM to implement FSMs. Like that was microcode, and I was like, oh, that makes sense. So it's a local bit of control, right? Like I have my BRAM, and I read from the BRAM to figure out where to read next in the BRAM or something like this. And I was like, can I use this to route data rather than just getting instructions? And I basically couldn't figure out whether I could use that idea to route, to do something other than fetching instructions or translating instructions and use it to actually route. But forget the BRAM and just have an FSM, like a real FSM instead of a BRAM FSM. Yeah, that's a good point. Anyway, we're 8 minutes over, so I definitely won't take anybody else's time. But if anybody has any questions for me, I'll stick around. But be shocked if anybody did.
So I guess one question would be, what would other than dealing with the performance issues, like what would have helped tool wise to shorten the design exploration loop for your problem? Like what would you like to know approximately that would have saved you a lot of work?
I mean, the same things that everybody's chasing, right? So there's a whole cottage industry of design space exploration papers, right? Like the folks at UCLA that are publishing, doing good stuff, Hanchen. So, the standard stuff, like I have my target, my real target, not like my local target because I'm having some problem with the tool. My real target is that 1 microsecond end-to-end latency. So, you're asking like a reasonable question, but I think I have the same answer as everybody else. So I'm trying to think of a more interesting one. I don't know. This is not an answer to your question, because everybody on this call, other than me, has really good intuition for when something's a register and when something's a wire. So I was going to say something like, I wish the tool would tell me without me going through synthesis and looking at the VCDs that, hey, like I know there's a set of rules, right? Like put it under, put it under, I'm forgetting the word, like, hey, the @ star or the @ pos edge clock, and use blocking or non-blocking assignment, and that's what determines whether it's a register or not. Like the register prefix, the register type means nothing, essentially, right? Or something like that, right? And everybody else has understood this and learned this and read the book or took the class or something. And me, who just jumped in and is like, I know how to write code. I'll just imagine it. I'll just interpret it, right? But ultimately, right, like the synthesis is what determines, right? So if there was some ahead of time, like syntax highlighting, like color this thing or whatever, but that might not be possible, right? Because the idea is, I said this to Skylar somewhere, like the idea is behavioral modeling, and the behavioral model isn't fixed until synthesis is done. So maybe that's just not known ahead of time or something like that.
Yeah, I mean, I think it's definitely clear that like almost every language layered on top always has like a real notion of a register and doesn't leave that for synth, that's not something you're guessing at.
Yeah.
Yes, and that's there. I think there's good reasons for that.
There's good reasons in the higher level languages, or they're good. So
Yes.
what I was
Right,
yeah,
like this is a first class right. State is a first class
Yeah.
concern in a system,
Yeah.
and having it be, hopefully you get the thing you want is just weird.
Yeah. So like, yeah, I don't know. I came at this from a really weird angle. Like I did an undergrad in math and physics. I never took a digital design or circuits or anything class. Like I knew what a register was, right? Because I know the CPU in my laptop has 32 of them or 60 or 100, whatever of them, right? So I'm like, register, state, cool. But then again, right? Like the behavioral modeling thing, you got to tilt your head and look at this stuff that you're writing when you're writing RTL differently than code. So maybe it makes sense. I don't know. You telling me that like, oh, this should be more explicit kind of makes me feel better about my confusion. Like, oh, I'm entitled to my confusion.
Yeah. I mean, all this only makes sense due to the history of the languages. I mean, VHDL was out of this like DoD VHSIC program, VHSIC, and that produced VHDL. And this was like, the DoD has a bunch of like microprocessor, like weird one-off like electronic circuits that's in like a tank or a plane or something. And we need to like document what these things do. So, hey, it would be awesome if we had a language for describing the behavior of this stuff. And then it was only later that people were like, oh, we can use this for synthesis. But there hasn't been a first-class effort in the other direction.
So I think I know this is true, but just double checking. There's no, I mean, I know that there's no IR, right? There's like analysis on and compiler passes on Verilog or VHDL, I guess for that matter, are done on the AST, right? There's no lower level representation. Is that correct?
In what, like every tool I can think of has an internal IR.
Oh, really? So even like the commercial. So okay.
Especially the commercial.
Yeah, interesting.
They're still in business.
Like you have to figure out what's going on, convert it to a form where things are explicit, so you can reason about them, and then from there get it to a form that's useful for whatever you're trying to do. Yeah,
cool. In that case, why don't they? Yeah, fine. So explicitness is possible. I don't know how many stages down the compiler pass pipeline it is, available. But like, yeah, okay. So why isn't it surfaced? Is it because everybody just knows and who cares? And why would you want that?
Yeah, so the other thing is like the things you can be explicit about in sensible high performance ways are a subset of the things you can do in Verilog. So, if you look at, VCS or any of the simulators, there's a bunch of things where once you start using them, like that part of your code has to revert to a more conservative implementation. Just because like it's encoding so much fine-grained detail in the Verilog that you have to be exceedingly careful to follow when you're simulating it. Whereas if like you have this bulk synchronous logic, like great, like we can jet that down to individual machine codes and do all instruction. We can do stuff. Is it okay? So maybe this is true, maybe it's not. Simulatable is not synonymous, is not equivalent to synthesizable, right? So my question is like, okay, cool, you flout and foil the simulators if you use this very precise or more precise, more conservative not representation, I don't know, whatever representation. Can you still synthesize it to logic? Like no. Most of Verilog is not synthesizable. The old Verilog specs had an accompanying spec, which was what subset of the language must be considered synthesizable. System Verilog has not had a revision of that spec. So it's not even defined what portion of the language you can use for synthesis.
So everybody
and
makes
vendors disagree wildly on what that subset
I was just about to say that, like, so you make it up as you go. If you go to some chip fab and they give you, well, so I'm talking about ASIC. I'm kind of drifting here between FPGA, but whatever, like drift between Intel and Xilinx, and they have different things.
They have different things, and certainly, like, just going through several years of Intel's tools, they vary for FPGAs. They varied on what they could synthesize from version to version. In fact, they varied on what they could synthesize within the same version for different chip families.
I think what's really funny about this is, so my affinity for this, like why I was interested in this project and this area and all this stuff was like, okay, cool. I want to get rid of all of the layers of abstraction that are foisted upon me when I program. I don't know, starting from Python and ending with like some instruction set, right? Like that all presupposes somebody else's ideas about what's good for me and what I want, how I want my compute to run, right? I mean, whatever, smart people that made wise decisions and some kind of cost benefit analysis went into that as well. But like, look, I want the least amount of abstraction possible. And then I get to Verilog and it's like, there's no rules. There's no spec. Make it up as I go. It's all abstract. You're not actually specifying anything. You're kind of like, you're implying, and then you're implying to the compiler, and then the compiler infers. Even the language is this kind of like philosophical take on the process.
Yes, and that basic problem is a very fundamental one if you are trying to make languages in this space.
Yeah.
Right, because like there's two views, right? There's this very behavioral view, which is, HLSs are a subset of that, but you can imagine a very much lower level behavioral view. Then you have this very structural view. And like Verilog does both, and you like mix them both in the same thing. And where those meet, there's lots of ugly weirdness.
Yeah, I don't know how you guys write compilers for this stuff. I mean, I don't.
Subsets.
Yeah.
Yeah, like you want to go down some rabbit holes. Structures as a whole, as a type, can be signed or unsigned. There's like you can add individual delays on wires, which you can't actually synthesize, but just like this signal is going to pop up sometime later. Like there's this whole set of stuff that is for testing that's cannot be synthesized. Or I can take a pointer to a wire, not exactly, but close. I can take a pointer to a wire and pass it around dynamically instantiated classes. That's in the language too.
Yeah. Not good. I mean, I don't know. Yeah, the industry survives and thrives and continues. Like obviously it hasn't kept people from designing new cool, interesting chips and making a crap ton of money on it. So can't be all, I'm not gonna be the naysayers like this is bound to fail. Of course it's not. So
yeah, but you're also not gonna make a modern web browser programming in assembly, right? Like it's technically possible. Yeah. But your tools limit the scale of what you can achieve.
Well, yeah, but I don't want to, I want to build a net that goes fast, and I felt like I should be able to, because all that there is it's a function. It's almost a pure function. The funny thing is it's not, right, because of time multiplexing. It turns into not a pure function, but like it's as close as math. It's as close to math as you can get in a program, and it's a really simple program too. So, I don't gotta show cat pictures to anybody.
Yeah, this is an unpopular opinion with sometimes when I share it, but the things you actually implement in hardware tend to, by necessity, be relatively simple.
Yeah, interesting. So I think you're implying that, like, you're implying some set of impediments. Like, hey, this stuff is simple because we don't have the languages to do better.
Partly, and like, what can you show is correct? And
yeah,
like, and also like as a substrate, what is hardware, raw hardware as a substrate good for doing?
Yeah.
I mean, I'll say I intimately understand the von Neumann architecture now. And that sounds weird, but like, I understand that you have to multiplex in time, and that leads to an instruction set architecture, because if you're multiplexing in time, you got to give a set of instructions, like you got to control, right? So like this thing that I had, I thought this was like a mythical thing. No, it's an accommodation of this limitation. Hey, if stuff's far away and whatever, I need to like cache things, cache instructions, whatever. Anyway, I'm kind of over talking and rambling, but so. So,
well, in the interest of time, shall we call it?
Sounds good.
And thank you.
Thanks again, guys.